So we've already seen that a derivative is really a rate of change, or what we're calling a slope. What's key in this unit is to understand that slopes have a specific function within the context of the real world. So when we're looking at an original function and we're talking about a real world problem, we can plug in an x value to get out a y value. And when I plug in another x value, I get a separate y value out. So I'm really finding the displacement between the 2 points. When we're working with real world problems and projectiles, we call this the position function, and the notation used is typically the letter s. I know it's different because you think displacement or position function, y, z, and s. That's just our standard calculation form. Now, when we're working with our tangent lines, what they're doing is if I look at the limit as the change in t goes to 0, the definition of the derivative from section 3.1, that gives me what we're going to call the instantaneous velocity, the velocity at that exact moment. Again, when we're looking at the projectile problems and the real world examples, the derivative at that point is going to be the instantaneous velocity. The average velocity would be just taking the slope here of that secant line between the 2 points. So average and instantaneous velocity are two different things. Average, think slope. Instantaneous, think derivative. And it's because if I'm doing a derivative, I'm finding the slope of a curve at a point. If I'm finding the slope of a secant line, I'm finding the slope between 2 points on a curve, but I'm approximating that slope as a tangent line. So if we're looking at this function and saying this is a position function here, what's going on with my instantaneous velocities? Well, I'm looking at traveling, and I'm traveling longer and longer and longer. And then what happens here is I flatten out. So if this is my car's position function, it's not moving between these 2 points. My car has been stopped. It's stalled out. And then it's getting back down lower and lower. So what's happening with this car is it's traveling further away from the starting point. It's sitting there, and then it's returning back to its starting point and passing it back up. So this is just kind of an illustration of what's happening with that position. It went 80 miles to the east, and you know that because it's up here at 80. Then it traveled 100 miles back to the west. So think about positive and negative numbers there. And I know it's 100 because it goes from 80 down to negative 20. The distance there would be 100. So what we start talking about is we have this position function s. Then we take the derivative of s, and that's our velocity. The absolute value of that is our speed. Why do we do absolute value? Because a velocity indicates movement backwards or forwards. If I have a negative 20 velocity, then that object is moving backwards. But if I'm talking about a speed, think about your odometer. There's no negative values because speed cannot be negative. That's why we take the absolute value of our derivative. And then acceleration would be our second derivative. So let's say we have a position function, x squared plus 3x. My velocity function would be 2x plus 3. My acceleration function would just be 2. So that tells us that we're driving at a constant speed because our acceleration is not changing something like 2x. So here's a position function, and it's for t squared minus 5t. My velocity function would be 2t minus 5. My acceleration function would be 2. And then I can use my graph to verify things. My velocity here at this point is going to be 0. So I'm traveling and I'm changing direction here because I'm decreasing and increasing. So I'm having this change happen. So if I look at my velocity function, I have 2t minus 5. My velocity graph is going to be a line, and that should make sense because when we differentiate, we're subtracting 1 from our exponent. So this would be a parabola because t squared. Our derivative is going to be a line, and our acceleration is going to be a constant graph because it's just 2. Now when I look here, I'm changing the ballgame a little bit because I have an initial position. So think about this as you're standing up on a ladder and you throw something in the air. If you're standing up on the ladder and you throw something up, it's going to make that nice arc, but it's eventually going to hit the ground. And I've got this nice position function. If I wanted to find out when it hit its maximum height, I would take that derivative and set it equal to 0. Why? Because the slope at a maximum it's going to have a horizontal tangent line and be 0. So I'm going to take negative 32t plus 64 and set it equal to 0. That's going to give me t equals 2. So if I wanted to know what the y-coordinate was for this point, I would plug 2 back into my equation, and I would get 160. This is also called the first derivative test, but anytime you want to find a maximum or a minimum, we're going to take that derivative, and we're going to set it equal to 0, because a maximum or a minimum always has a tangent line that has a slope of 0. Now, once I'm looking at the line for my velocity, I have this constant line happening. There are no maxes or mins here. But I am crossing the axis going from positive to negative values. That's telling me the stone is arcing up because it's positive, it's increasing. And then it's negative, which means it's decreasing. So if I think about that projectile, increasing is up, decreasing is down. So here's another example of a graph. What's happening here is my internet users is increasing every year. So I should expect my derivative to be positive or above the axis. So it should make sense that this is my derivative graph. I'm going from a parabola-looking curve to a line because of that power rule. I have a cost function. What do I know? This is a linear function. So my cost function is going to be a constant. It's going to be a horizontal line because I have only one x. The derivative of 500 is 0. The derivative of 0.1x is going to be 0.1. Now this is going to be a little bit different. I have 500 over x plus 0.1. The good news here is that in this graph, 0.1's derivative is going to be 0. The bad news is I may have to use a quotient rule, but I want to take a minute to illustrate what you could do instead of using a quotient rule here, okay? I personally like to avoid the quotient rule, and I will do a lot of things to avoid the quotient rule. What I can do here is I can make that 500 times x to the negative 1. So if I'm trying to differentiate that, if I want to avoid that nice quotient rule, I can take 500 over x, and I can make that 500 times x to the negative 1. Then I can use my power rule and take the negative 1 to the front, and that gives me negative 500. Then I'm going to subtract 1. Negative 1 minus 1 is negative 2. So to get that back in a fractional form, because we never want to have negative exponents, that would be 500 over x squared. And there is my full derivative. Now again, there are multiple ways to get to an answer in calculus. Some of you may prefer to do the quotient rule, and that's okay. It's just something that I like to avoid as a personal fact. So when we start talking about average cost and marginal cost would be the derivative, and my average cost is I'm taking my cost and I'm dividing it by x to find that per unit cost. So you want to take these down in your notes, and you want to make sure you're given a cost function. If I want to know the cost to produce a specific number of items, I would divide by the number of items. That should make sense. If I buy 12 packs, if I want to find out how much I paid for each 12 pack, I would divide the number I paid by 12. But marginal cost, that keyword marginal, is going to tell you to take the derivative. So if I have cost function and the number of items, and I'm looking at the graph of the marginal cost, I'm going to take that 2, bring it to the front, plus 50, and I'm going to get a different kind of graph. If I want to look at the average cost, I'm going to divide every term by x. So when I divide everybody by x, I have x squared divided by x, 50x divided by x, and 100 divided by x. There's my average cost function. And again, if I'm doing the marginal cost, I'm going to go back to the derivative. 2 times negative 0.02 would be negative 0.04x, and 50x derivative of that would just be 50. So if I have supply and demand, I should notice this is a linear function. So the derivative of a linear function is going to be a constant function. The derivative of 1200 is 0. The derivative of negative 200p is going to be negative 200. So now we have the chain rule. The chain rule, a lot of times we need to see it in action. So the chain rule happens when we have like a nesting doll situation. I have one function inside of another. So it's like f of g of x, the composite functions. And what it basically says, this notation is a lot to take in, I know. We move from the outside to the inside taking derivatives. What does that actually look like? Okay. So let's say I have x squared plus 4x raised to the 5th power. This is a nesting doll, right? This would be u to the 5th, and then I put something inside. I put x squared plus 4x there. So when I do this, I'm going to take the derivative from the outside in. I'm going to bring the 5 to the front. So I get 5 times x squared plus 4x, and I'm going to subtract 1. So I get to the 4th power. Then I'm going to multiply by the derivative of the inside, which would be 2x plus 4. Now, in the lab, we're not going to look for you to actually FOIL this out to get the big long answer. We do want them fully factored. So this would be as far as I would take it, because I would take it as fully factored. So there's a lot of notation that happens. Now, when they give you a table, you can do the same thing. Let's say I'm working with f of g of x. So we said we're going to take the derivative of the outside, and we're going to work our way inside. So that would be f prime g of x times, but notice when I did the previous one, I didn't change the inside, I just brought the 5 to the front, the derivative of x. So I can go into my table and actually replace these with values to find the actual derivative, even though I don't have a function. So when I'm doing that, I'm going to have my f prime of g of x, and I can multiply that by my g of x. So typically when we see a table like this, we would see something that would indicate f prime of g of x. So I'm looking at f prime, which would be when I plug in, let's say 1, I get 5. So let's say I have this situation. I'm wanting to evaluate this at 1. So I'm going to go into my table and say, okay, what is the g of 1? Well, the g of 1 is 2. So this would be f prime of 2 times the g prime of 1. So g prime of 1 is 3. Then I'm going to go into my table. What is the f prime of 2? It is 7. So I get 7 times 3, which is 21. And these questions are often ones that are overlooked. They're not overly difficult, but you have to take them step by step with the derivative, even though you don't have an equation. So I know when you start to see these in a lab, you think, I don't have an equation, how can I do this? You're actually going to symbolically take the derivative, and then you're going to use your table to actually determine the derivative. Now this is just another expression of the chain rule for powers. This is exactly the example that I just worked, but we're going to be using a formalized rule here. So if I have this function, sine of e to the 1/3 cosine x, this is a chain rule. I do have multiple things going on. I'm going to take the derivative of the outside. We haven't really learned trig functions yet, so I'm not going to fully work this example out, but once we get to next week, you should be able to do this. So I would take the derivative of the sine, I would recopy the inside, then I would take the derivative of e to the 1.3 cosine x, but we haven't quite gotten there with our trig functions yet. So let's look at one more example of the chain rule. It was one that I come up with, just to kind of help it click, because we haven't seen trig functions yet, and the majority of the time we're going to see this used is going to be next week when we see those nice trig functions. So let's say that I have e to the x squared plus 4. This is considered a chain rule because this is e to the x, but I've replaced x with x squared plus 4. So I've got that nesting doll situation. So what is the derivative of e to the x? Well, the derivative of e to the x is e to the x. So I'm going to recopy my derivative. Then the chain rule says to multiply by the derivative of the inside. So we're thinking of this like it's e to the u. The derivative of e to the u is e to the u. Now I'm differentiating u. So I'm going to get times 2x, because the derivative of x squared is 2x, and the derivative of 4 is 0. So writing this fully simplified would be 2x times e to the x squared plus 4. So pay attention to the main mistake that's going to be made here, as this is going to be differentiated. A lot of people forget that you recopy when you're doing the chain rule. You don't actually differentiate it. So just keep in mind, as we're doing the chain rule, you're recopying your g of x and then multiplying by the derivative.